Hi, everybody. Thank you for joining us for the International Indian Statistical Association's Statistics and Data Science Innovation Series, webinar series talk. Uh, this month, we have Dr. Anindya Bhadra. Dr. Bhadra is an associate professor in the Department of Statistics at Purdue University. Dr. Bhadra's interests are Bayesian methods for high dimensional and complex data, computational statistics, with applications in life sciences, including genomics, nutrition, and infectious diseases. Dr. Bhadra has also been the Young Statistical Scientist awardee by the International Indian Statistical Association in 2021. And today he'll be talking to us about graphical evidence. And just a note that this talk is being recorded. Um, Anindya, it's all yours.
All right. Thanks, Sharik and Jyotishka, for the invitation. And it's always my pleasure to give a talk to the IISA. That's always special. So as you can see, this talk has a very short title. It's called Graphical Evidence, but it's let me see if I can move my slides. Yeah, it's see, the title is not very informative. What it is really about is it is about marginal likelihood calculation. Okay, so another name for that is evidence. And in particular, I'll be talking about marginal likelihood calculation in Gaussian graphical models. Okay, so hence the title, Graphical Evidence. So first of all, why marginal likelihood? So if you are a Bayesian, you probably don't need don't need to be convinced why this is important, but because that it forms the basis of, say, Bayesian hypothesis testing, right? Via Bayes factors or fractional Bayes factors. You need it's exactly the ratio of marginal likelihoods. If you are not a Bayesian, you can evidence or marginal likelihood is still useful, right? You can think of the classical, for example, the James-Stein estimator. So what you do is that you calculate the marginal likelihood and then you select the variance parameter by maximizing the marginal likelihood, and that gives one way of tuning prior hyperparameters. Okay, so that's empirical based. It doesn't have a full Bayesian interpretation, but it might still have good frequentist risk properties, as we know, from the properties of James-Stein estimator. So evidence or marginal likelihood is important for various reasons. And because of this importance, there exist many generic approaches. Okay, so it's not that in 2022 we are suddenly realizing that marginal likelihood is important. So there exist generic approaches, but I'm going to argue that the calculation of evidence is actually mostly unresolved in Gaussian graphical models. Okay, it's not completely unresolved. It can be there exist closed form formulas for very specific priors, such as the Wishart prior or some special cases under the G Wishart. But in general, if you want to move beyond those types of priors, evidence calculation is still intractable, and the common approaches are very difficult to apply to the extent that we don't know how to apply them. And I will make it clearer what the difficulty is. Okay, so the goal of this talk then is to provide a tractable approach for evidence calculation or marginal likelihood calculation in GGMs under fairly mild requirements. And what those requirements are, I will also make it clear as I go along. And before proceeding further, let's give credit where it's due. So bulk of this work is done by Shiraz Sagar, my PhD student at Purdue, who has been extremely productive and is just about to graduate this year, and with a PhD. And then Shantan Banerjee at IIM Indore and Jyotishka Datta from Virginia Tech, who is also a co-host of this seminar. Okay, so moving on. So then let's introduce just the very rudimentary notations that we need. So this is the notation that we'll be using throughout the talk. Okay, so Y is n by p. So n is the sample size, p is the dimension. So, and then so basically you can, the ith sample is a p vector, p dimensional vector, and that's coming from a multivariate normal. We are going to assume the mean is 0 throughout. It's a 0 vector of length p, and there is a precision matrix. Okay, that's omega is the precision matrix, not the variance matrix. That's p by p. Okay, so that's very standard notation. And if you want to write the entire matrix as n by p, then you need this Kronecker product of in and then omega p by p inverse. So we are not assuming any correlation among the samples, okay, hence the in. And then with that notation, then evidence calculation. So this is simple in principle for not just for this model, but for any model really. It's just an integral, all right? So the first term is the likelihood if y given omega. The model is parameterized by omega, remember. And then you have a prior on omega that so all densities, I'm denoting them by f, okay? So what you do is that you multiply the likelihood and the prior, and then you integrate out the prior parameter, and then the resulting quantity will involve the data y and whatever the hyperparameters of this prior in omega are. Okay, that's the marginal likelihood. So all the random parameters have been integrated out. The fixed hyperparameters leave, and that gives you the marginal likelihood. So again, if you can think of in the James-Stein situation, where you integrate out the theta, and then the marginal likelihood becomes sort of like y is normal 0, 1 plus tau squared, the prior variance squared, etc. So that's marginal likelihood. So here, what is the difficulty in GGM is this restriction, okay? So for your prior to be valid, the prior mass must be restricted to the space of positive definite matrices. If you put mass anywhere else, then it is not a valid prior for a precision matrix, okay? And that causes a lot of difficulty. So it's not just a simple matter of integrating over the real line or over the positive real line and so on. You have to integrate over this space of positive definite matrices. And this is the crux or the source of all difficulties, so that unless your prior has sort of very specific structure, such as Wishart, or there is a recent paper in the Annals of Statistics by Caroline Euler and co-authors. So there are specific instances of G Wishart, which is another prior, another conjugate prior for Gaussian graphical models, but very specific cases under G Wishart, not all kinds of G Wishart, okay? And because of the same reason, now we can sort of begin to see what the difficulty lies. So suppose I would try to use something like bridge sampling or path sampling or even importance sampling to estimate the marginal likelihood, right? So those are all valid approaches. So in order to use, say I'm using importance sampling, what I need is a covering density. I need a density, okay, that will have, in some sense, that will cover the entire support of f omega, and it will have thicker tails and so on. So that's actually very hard to design under the positive definite restriction. Okay. So, and if the covering density is not well designed, its elementary calculations show that importance sampling estimate has infinite variance. So this positive definite restriction is the source of all difficulties, and it's not just here. It's anywhere you have to deal with positive definite matrices, this difficulty is going to show up. So Gaussian graphical model is one. Gaussian process where you deal with design of new covariance functions, not covariance matrices. They have the same difficulty. They get into a lot of trouble for this positive definite restriction. All right. So then, what can be done? So first, let's talk about as I mentioned at the outset, that evidence or marginal likelihood calculation is not a new problem, and it is clearly important. So there exist generic approaches. Okay. And when they apply, it's fine to go ahead and use them. So in this slide, this is sort of a one-slide non-exhaustive summary of some of the popular approaches. So the first thing is that you can use the so-called harmonic mean estimate by Newton and Raftery, the JRSSB paper. And there are some variants, instead of using a plain harmonic mean, you can use sort of a weighted version of that. That's by Gelfand and Day. It's easy to show that under very mild conditions, these estimates will have infinite variance. Okay, so that's harmonic. Not just in Gaussian, nothing to do with Gaussian graphical models. They will have infinite variance in pretty much in many other models as well. There exist importance sampling approaches, and within that, that's an importance sampling is an umbrella term here. Within that, there exist subvariants such as bridge sampling by Gelman and Meng. And then there exists sort of warped version of bridge sampling by Meng and Wang, and so on and so forth. But again, bridge sampling is sort of a subclass of importance sampling. So again, you need a covering density, which is hard to design under a positive definite restriction. there exists an approach by Radford-Neal. This is interesting, annealed importance sampling, which essentially samples from the prior and then sort of creates an annealed version of the prior itself. Okay, so that one is actually a little bit more interesting, a little bit more broadly applicable. There exists nested sampling by John Skilling. So what this does is that you sort of have to sample from progressively. It's an iterative procedure. You sort of have to sample from progressively higher likelihood region. All right. So that's how it's an you are essentially you are calculating an integral. It's an and then it's a Monte Carlo estimate of the integral. So hard to design, hard to implement in high dimension, not just in graphical models, because finding that high likelihood region in p-dimensional space when p is very high is very, very difficult. Most of the likelihood region is going to be empty or we have pretty much close to zero mass. There exists a method by Cheap and Jelyaskov that's actually based on MCMC posterior draws. So Cheap's method is great because the thing is we don't need a covering density. Okay, for Cheap's method, I'm going to give a bit more detail. So long as you have a valid Markov chain Monte Carlo sampler, Cheap's method will apply, provided some analytic calculations can be done, and we'll make it clearer a little bit in a little bit. Okay, so if you're interested in evidence estimation in general, the excellent review article that just came out in SIAM Review by Llorente et al. I encourage you to take a look. Okay. So this then is some of the generic approaches, but then the question is, do these work for GGMs? Do these work? So let's see. So this harmonic mean estimate, as we know, it can have unbounded variance. And the reason that happens is that it can be shown theoretically. There is a paper by by Olpert and Scott Schmeider, that shows that if you calculate the if you calculate the limit distribution of these of the harmonic mean estimate, okay, when when the sample size is large and so on, and then the limit distribution is alpha stable, okay, and oftentimes this alpha will be less than 1, and if it is alpha if you have an alpha stable distribution with alpha less than 1, no moments will exist. Okay, so it will have not only have it will have infinite mean, not just infinite variance and so on. We are not aware of choosing any principled way of choosing an importance or bridge density. So this covering density that you need, it can be done if you have to design a covering density, say a univariate normal distribution, right? I can cover that using a Cauchy distribution. Why? Because a Cauchy distribution has heavier tail than a normal. Okay, so it's a reasonable covering distribution. But here, first of all, I have to do it in a multivariate setting, and then I have to do it while being restricted to the class of positive definite matrices. Okay, so therefore we are not aware of any known ways of doing this. Nested sampling that I mentioned, it requires sampling from a progressively higher likelihood region. Okay, so in the first iteration it will go through. You just sample from wherever you are, but then you sort of take out that part of the likelihood surface. You try to move to another part of the likelihood surface that has a higher likelihood. And this is very, very hard in high dimensions, because no matter where you search, most of the likelihood surface has close to zero mass. And a case in point, this is not a proof or anything, but it's just I would just like to make this point, is that there exists a specialized Monte Carlo method by Atay, Kais, and Massam. There is a 2005 Biometrica paper for computing evidence or marginal likelihood under G. Wishart prior, that appeared about a good 10 years after the generic approaches such as harmonic mean estimate and bridge sampling and path sampling. Most of those approaches appeared in the mid-90s. So if those things worked, okay, for Gaussian graphical models, there probably would have been no need for a Biometrica paper tailored specifically to a G. Wishart. But this paper only can handle G. Wishart. It won't work with other kinds of priors. So in this talk, we are going to focus on Cheap's approach. So let's try to understand a little bit what Cheap's approach is. I sort of made a point that whenever we can do MCMC, Markov chain Monte Carlo, we can do Cheap's approach, and it will give good result. So why is that? So what is the approach built on? So let's So here are some of the details. So what I have here on the first bullet point is simply a restatement of Bayes' theorem. Okay. So under any model, the marginal likelihood can be denoted in this way. Okay. So we are typically used to see this denominator on the left-hand side and this Fy on at the bottom here. Okay. So then that is just a restatement of Bayes' theorem. So it says marginal is equal to likelihood times prior divided by posterior. So the likelihood and the prior are something we decide as modelers. So typically, suppose we, the likelihood cannot always be evaluated, but suppose to make things simple, suppose we have chosen the likelihood and the prior in a way that they can be evaluated at some theta equals theta star. The trouble now is that if you want to estimate evidence, Fy, you need to evaluate F theta given Y. It's not a matter of simply sampling from F theta given Y. So I want to hammer down on that point, that sampling from a distribution and evaluating, sampling from a density and evaluating a density are two totally different things. Okay. If I needed to sample from F theta given Y, I only need an unnormalized version of that density posterior. Okay. And that's the premise of Markov, Metropolis Hastings and all other, many other Markov chain Monte Carlo techniques. But here, I need to be able to evaluate F theta given Y, meaning I may not ignore the normalizing constants of F theta given Y. Okay, so that's the source of all difficulty. Now, if you have the normalizing constant of F theta given Y, then you don't need any other method. Just your calculation is analytic, so just go ahead and do it. But as most Bayesian, any Bayesian will tell you that the normalizing constant of the posterior is often intractable. Okay. And that's the interesting situation. So this is what Chip handles. This is Chip's innovation. So what does Chip do? Chip's strategy is very clever actually. So what he does is that he decomposes the entire omega. Omega is the entire parameter into two parts. Okay, z and theta, where z is the nuisance parameter and theta is the parameter of interest. And then you run a Gibbs sampler as usual, iterating between z given theta comma y, theta given zy. Y is the observed data, so everything is conditional on y, and that will eventually converge under standard MCMC mixing conditions to the joint fz theta given y. Okay, and if it converges to a valid joint, it will also have correct marginals separately for z given y and theta given y. And then what she will do is to estimate this f theta given y in this way. It's simply a Monte Carlo estimation of f theta given z comma y, where the ith sample of z is coming from the Gibbs sampler, because that's what the Gibbs sampler provides, right? That's what the Gibbs sampler provides. So what's the benefit? The benefit is you need the constant for f theta given zy, not the other part of z given theta y. So now why is this beneficial? So imagine this f theta given y, suppose it's a t distribution, all right? So if it's marginally a t distribution, I can certainly write it conditionally as a normal distribution subject to some mixing inverse gamma scale variable and so on. Okay, so this is often the case. This is the basis of data augmentation and everything else, that the normalizing constant of f theta given y may be intractable, but the normalizing constant of f theta given zy, conditional on this z, may be available. Okay? And that's what Chip exploits. So the key is this decomposition. This decomposition has to be done in an intelligent manner, such that at least for the parameter of interest, the normalizing constant is tractable. For the other part, f z given theta y, you don't need the normalizing constant. Why? Because we are going to merely sample from it. We are never going to evaluate the other density, f z given theta y. Is this clear? Are there any questions about this? Okay. So this is the crux of Chip's method. Okay, it's very clever. So what are the benefits? So Chip's approach is automatic in the same way a Gibbs sampler is automatic. Okay, it's based on a Gibbs sampler. And you don't need an explicit choice of a covering density. You don't need an importance density. You don't need a bridge density, and so on and so forth. So that's a very big benefit, to be able to do something in an automatic manner in this, under this positive definite restriction is very beneficial. But applying Chip's method, it will require a suitable f theta given z comma y that can be evaluated. This is the parameter of interest, theta. Okay. The other thing, z given theta y, need not be evaluated, but this part must be evaluated, and hence it's in red. And merely sampling from it is not going to be enough. Okay. And then, therefore, application is a matter of art. You have to introduce this latent z in a certain way such that the the normalizing constant of theta given zy becomes tractable. Okay, so it's not generic in a way. The harmonic mean estimate is generic or a black box approach. And there exist some known difficulties in finite mixture models that were pointed out by Radford Neal that we are not going to go into because we are solely going to deal with continuous mixtures. Okay, so that's Chip's approach generically. What do we do? How does it apply to GGMs? So suppose we work with this decomposition, all right? So we have this omega, that's a P by P matrix. So we simply decompose the matrix in this way. And I hope it is self-explanatory. So this omega P minus 1 by P minus 1 is the upper left P minus 1 by P minus 1 block. Omega dot P is a vector of length P minus 1, and then omega PP is a scalar. Okay, so this omega dot P, omega PP, which together I'm calling theta P, it is simply the last column of omega P by P, right? And then by Z, I'm calling, I'm collecting all the other latent variables into Z. Okay, so now we are going to see how we can apply Chip's method to GGMs. And then there exists a paper by Wang in 2012 Bayesian analysis who showed in the context of sampling. Okay, so Wang didn't deal with likelihood evaluation, but he showed in the context of sampling that if this is your definition of theta P, which is the last column of omega, then under certain priors, you can actually decompose the off-diagonal elements, the conditional posterior of off-diagonal elements as normal, and the conditional posterior of the diagonal element omega pp as gamma under suitable priors on omega p by p. Okay. So basically, so what are these suitable priors? So essentially, Wang showed it for some prior called Bayesian graphical lasso, but we realized that for this to happen, all that needs to hold true is that the prior on the omega pp terms are either gamma or mixtures of gamma, because that has to be a positive variable, and the prior on omega dot p are either normal or some scale mixtures of normal. Whenever that is true, you can apply Wang's method. Okay, and Wang did it for sampling. We are going to do it for density evaluation. Okay, why is that? Because the normalizing constants of both normal and gamma densities are available. So this is actually not something that Wang needs. Even if it is normal times gamma, so he just needs to sample, okay? But for us, it's crucial that the normalizing constants for this last row and column, conditional on everything else, is tractable under very, very mild conditions. So let's see how we do this. So this is now my just a restatement of Bayes' theorem, okay, also known as candidate's formula. So log marginal is log likelihood. Remember the parameter now theta p is the last column of omega p by p. All right. So log marginal is log likelihood plus log prior minus log posterior. All right. So now this thing here, this likelihood, this is not likelihood of y omega y1 through p given the entire omega p by p. Okay, that's multivariate normal. But what I have here is theta p, which is just the last column. So this is an integrated likelihood. All right, this is not a multivariate normal. So how to make use of this? So slightly rewrite the first line in this way. So the left-hand side is identical. I'm decomposing the first term, okay? F y1 through p given theta p, write it as condition on y1 through p minus 1, okay? And then the conditioning on theta p remains, and then the second plus the second term, the marginal of y1 through p minus 1 given theta p. And the log f theta p remains as it is, and the posterior remains as it is. And I'm giving this, there are 4 terms, I'm giving them some names, 1, 2, 3, and 4. And now my goal is likelihood evaluation. So I have this entire omega, right? And because I have the entire omega, I also have theta p, which is the last column. So let's see. So the first term, this term here, I can evaluate, right? This, because theta p is just the last column of omega p by p, and I'm conditioning on the remaining y's. So this is nothing but a partial likelihood evaluation under a multivariate Gaussian, which we know is this univariate normal. So the term 1 can be evaluated. Term 3 and 4, they are prior specific. We will deal with them later. The problem there now, any questions about, are you convinced that the first term can be evaluated at least in this decomposition? But the problem is now, what is the benefit? We had one integrated likelihood here, y1 through p given theta p. Now we ended up with another, y1 through p minus 1 given theta p. So even if I can evaluate the first term, 1p, I still have to deal with 2p, right? So is there a benefit? So here is the main innovation of our approach. So what we did is that after doing some manipulations, we found out that there is actually a very nice telescoping property of the second term. So this is the second term from the previous slide, 2p. we will do a further decomposition. So it's y1 through p minus 1 given theta p. Now condition on y1 through p minus 2 given theta p and theta p minus 1, where theta p minus 1 is the p minus 1th column, row or column of the entire omega matrix. And then so basically just a decomposition of the of this term. So it's the usual same decomposition that we saw on the previous slide with p replaced by p minus 1. And again, I end up with 4 terms, call them 1p minus 1, 2p minus 1, 3p minus 1, and 4p minus 1. And now, look, this first term here, again, looks like a partial likelihood, does it not? Again, I have yp minus 1 conditioned on y1 through p minus 2, given the last 2 rows and columns, but with one catch, with one caveat. It is a partial likelihood of yp minus 1, but not yp minus 1 given rest. The rest will include y1 through p minus 2 and yp. There is no conditioning on yp, okay? So therefore, you cannot use the original omega, cannot calculate the partial likelihood based on that. What you have to do is that you ended up with this p minus 1 by p minus 1 block. That's the original, from the original omega. You have to do a sure complement adjustment of that. That's sort of it's a specific instance of iterative proportional scaling. So what you do is that you take the original p minus 1 by p minus 1 block and subtract from that this omega dot p transpose divided by omega pp. So this is only a function of theta p, the last row and column. And if the original omega was positive definite, this calculation will maintain the positive definiteness. Just because, if you have a positive definite matrix, sure complement of any submatrix of any upper left diagonal block is positive definite. So you calculate that thing, and now this thing is positive definite because and then we have this, right? The omega 1 through p minus 1 given all the parameters is actually normal with this omega tilde. So it's not omega 1 through p minus 1 is not a normal with omega p minus 1 by p minus 1. It is a normal with omega tilde p minus 1 by p minus 1, which is a sure complement adjusted version of this. So with this, we can actually evaluate the first term. All right. So 2p is something plus 2p minus 1, and then 3p and 4p, and these terms 3 and 4, they will be evaluated, so on and so forth. But this is the thing. Now we are in business. This is what will continue. So the thing is, now it provides the overall strategy. So we know how to evaluate term 1. We will talk about evaluating term 3 and 4 in a minute. Those are prior specific. The problem lies with term 2. That's the integrated likelihood. There is no direct way to evaluate it. You can try to brute force it, but what we do is that we simply get around it. We never evaluate it. We simply use the telescoping property. The log marginal, this is from the first slide, and then it has 1 plus 2 plus 3 plus 4, and 2p is 1p minus 1 plus 2p minus 1, and so on and so forth. And then we simply proceed row by row or column by column, and the term 2, which is the problematic term, simply cancels from the overall sum. Never actually needs to be evaluated. The only things that need to be evaluated are the terms 1, 3, and 4. So this is the strategy then. So what you have is the entire omega. The last row and column that's in purple, that's theta p. So calculate the first, 1p, 3p minus 3p and 4p using the last row and column. Then do your sure complement adjustment. Now you're in the green column. Calculate 1p minus 1, 3p minus 1, and 4p minus 1, and proceed in this, from the south, proceed from the southeast to the northwest direction. Okay, and if you do this, positive definiteness is guaranteed at every step, and the second term never needs to be evaluated. So the overall strategy is this: run cheap p times, adjusting omega by a sure complement adjustment, the remaining p minus 1 by p minus 1 block at each time. So first time you run cheap, you take out the last row and column. Then you run cheap, you take out the p minus 1th row and column. And at the end, only the omega 1, 1 that is left. And in each equation, evaluate only 1, 3, and 4. And the term 2 is problematic. Don't just get around it. Don't try to brute force it. Eliminate that by a telescoping sum. Now, obviously, this is only true if it's exactly 2p here, if it's exactly 2p here. But remember, in each equation, we don't have the exact quantities. What we have is their estimate given by chip. So clearly, then their bias will add up if your p is very large. But still, it will be a linear quantity in p, and that bias is a function of your Monte Carlo, the number of Monte Carlo samples that you have, and so on and so forth. Are there any questions? This is the main slide actually of what we have been trying to do. Okay, so then term one is a partial likelihood evaluation. So this calculation of the first term is independent of whatever prior I have on my omega, okay? Because it's partial likelihood. It's conditional on theta, which is a submatrix of omega. So now we have to get into term 3 and 4. So all this business will be moot if we cannot calculate the third and the fourth terms. So these are prior specific, okay? So these are prior and the posterior terms respectively. So let's see, how can we do this? And under what kind of priors can we do this? So first, but does any of this work? How do we know if any of this works or not? So let's take an easy case first. So this is the Wishart prior, okay? So this is Wishart is a special case I mentioned at the outset for which you can actually have an analytic expression for the marginal, all right? So if you have your omega has an Wishart prior with a positive definite scale matrix V and some parameter alpha, then the log marginal has this closed form expression. As you know, y given omega comes from a multivariate normal, and this is the prior on omega, then this is the log marginal likelihood, all right? So it's an analytic expression, so we can compare against it, all right? So it's sort of our simulation study, the known example. But does our technique work? So remember, so we have to calculate the third and the fourth terms, right? So here is a recap of what the third term was. The third term was log f theta p, where theta p was the last column of omega p by p. And it turns out in Wishart, if you have an Wishart matrix on the entire omega, then there exists a property that the density of the last column of omega dot p comma omega pp can be it obviously can be written in this way by conditioning on omega pp first and then the marginal of omega pp. And it turns out it's simply the omega dot p given omega pp is simply a normal, okay, with variance omega pp, and the marginal of omega pp is just a gamma. So computing the third term is easy. It's just if I give you the values of the theta p at some theta star p, all you will do is that you will evaluate a normal and a gap times a gamma density at that theta star p. This is from the property of Wishart. But still remains the term 4p. All right, what to do about 4p? So this is what we do about 4p. So you can decompose S, the sample variance covariance matrix Y transpose Y, analogous to omega, and you can reparameterize S in this way. Okay, like the same thing, P minus 1 by P minus 1 block, S dot P, SPP, and so on. And then we just reparameterize the theta P, the last row and column a little bit. Okay, so what we do is that we introduce these two new variables. Beta dot P is the same as omega dot P. So this is the off diagonal elements in the last column of omega. And gamma pp is omega pp, which is the last element, the p by p element of the original omega, minus this thing. Okay. Again, it's a Schur complement adjustment of the bottom right 1 by 1 block. So if omega pp was positive, this gamma pp is also going to be positive. We can see that by using properties of Schur complement. And there is a key result of Wang from the Bayesian graphical lasso paper, who showed that under this reparameterization, the conditional posterior, not the prior here anymore, the posterior, meaning everything is conditional on the data y, is also a normal times a gamma. And this is what he used for sampling from the Bayesian graphical lasso prior. Okay, where so this is just a simple normal, this is just a simple gamma. Okay, so that's all you need to do. So first we sample we evaluate a multivariate normal density, then adjust this thing, and then evaluate basically a truncated gamma density. It'll be a truncated gamma. So this then this reparameterization also allows us to compute the fourth term using Cheap's two-block strategy, at least for the last column, okay, 4p. Any questions about this? And then finally, all that remains is to proceed backwards in that direction. So cycling through the columns from p minus 1 all the way to the first column. So 3p minus 1 to 3,1 and 4p minus 1 to 4,1. So it's the same strategy as going from what we use in going from 1p to 1p minus 1. Okay, so proceed backwards starting from the pth row. At each step, adjust the upper left j by j submatrix, and forget about the rows that lie ahead. All right. So this is the adjustment for j equals p minus 1 through 1. Proceeding backwards, update the upper left j by j block as the original j by j block minus its Schur complement. And if you do this, you can see fairly easily that at every j, you will maintain positive definiteness. That is guaranteed. And then we calculate 3j and 4j in an identical manner 3p minus 1 and 4p minus 1 in a manner identical to what we use for 3p and 4p. Still a normal times gamma in the prior and the posterior. Okay, so these are the results for Wishart. So here the truth is known. Okay, so for various dimensions and various parameters for alpha. And this is the proposed approach. And we compare with two things, annealed importance sampling and then nested sampling upscaling, because these are the two things that still work somehow under positive definite restriction. Bridge sampling and things like that don't even, we don't know how to do bridge sampling because we don't have a covering density. So only, up until about dimension 25, the results are about perfect, 2417, 2417, okay, differing in fraction. Only at p equals 30, we start to see maybe a little bit of bias. Some of the other competing approaches, they basically, they just give up. So it becomes numerically, it goes below machine precision, and likelihood becomes 0, and the log likelihood becomes negative infinity. So okay, so it's not theoretically negative infinity. It's just that AIS and nested sampling has gone below machine precision, and even at lower dimension, the other competing approaches are badly biased. So this is actually a feature of CHIP's technique. When it works, CHIP is great, right? Because it's based on MCMC posterior draws, and you are sampling from the posterior. So that means there was some posterior mass there, and the posterior can only be non-zero if the likelihood was non-zero to begin with. If the likelihood was 0, the posterior there is also going to be 0, right? Because posterior is likelihood times prior. So that's actually a very beautiful property of CHIP's method. But what was unclear was how to do CHIP's method for Gaussian graphical model under this positive definite restriction, which we have resolved. But so far just Wishart, right? So clearly, Wishart is our simulation case. If the truth is known, obviously why we need to do this, right? So clearly we did not get into all this trouble just for Wishart. So let's see, what are the other types of prior we can handle? All right, so consider this type of prior now. It's just an element-wise prior. So I have some, prior on the off-diagonal terms, omega ij, and some prior on the diagonal terms, times this indicator, that the entire omega lies in MP plus, okay? I can certainly write a prior like this. Of course, it's a very complicated restriction. So what I'm doing is that I'm putting element-wise prior, and then I'm putting a truncation. Like think of defining a truncated normal density. You just write the normal density times the truncation, right? I.e. x greater than 0. Same thing in the space of p by p positive definite matrices. So of course, if you do this C will be very complicated. So that's what we are after. We'll calculate the marginal likelihood. So two examples of this type of priors have recently become very popular. Two examples I will give. One is the Bayesian graphical lasso, so whose sampling method inspired sort of our approach, so to speak, which puts this kind of, on the ijth element, the off-diagonal elements, it puts a double exponential prior. So it's sort of a sparsity-inducing double exponential prior, which has a normal scale mixture representation by the classic result of Andrews and Mallows, meaning if marginally f omega ij is a double exponential, then you can bring in some latent variable tau ij, conditional on tau ij, it's a normal, and tau ij is an exponential. All right, so that's the scale mixture representation of the double exponential. And there is the graphical shoe prior, which my student and I developed a while ago, which essentially uses sort of this type of normal scale mixture of half Cauchy on the off-diagonal terms, which is known as the horseshoe prior. Okay, that has sort of better shrinkage properties than the double exponential. But they both, the key point here for our purposes is that they both fall under the framework of normal scale mixture, all right, for the off-diagonal terms. And for the diagonal terms, then we are just going to use simply an exponential. Because the diagonal terms have to be positive, right? So here is the prior then. The off-diagonal omega ij terms, they are normal now, conditional on this tau ij. That's the difference with Wishart. In Wishart, they were truly normal. Now they are normal, conditional on these component-specific tau ij terms. And similarly, the omega jj terms are exponential, just as in the Wishart case. So what happens is that for our purposes, these mixing variables, these tau ij variables, is the only difference with Wishart. If it is normal times gamma, we are in business, correct? Now the key thing is that these tau ij terms, the latent mixing variables, they can be sampled easily. And that was what Wang derived for Bayesian graphical lasso, what we derived for graphical horseshoe. The trouble will come if you try to evaluate that density of the tau ij given rest, the density evaluation. Well, we'll never do it. The main idea is that it's cheap, right? So we have this theta z decomposition anyway, parameter of interest and latent. the parameter of interest theta, that density has to be evaluated. The density of the latent z never has to be evaluated. You need to be able to sample from z given rest. So the main idea is that you have these latent mixing variables tau ij, no problem. Just absorb them into chip's latency. Meaning we are going to sample them, but we are never going to evaluate their densities. And conditional on them, provided they have been sampled, we are simply going to evaluate the normal and the gamma densities exactly as we did for Wishart. And now you see the benefit. Just think about how many priors you can represent as scale mixtures of normal, right, for omega ij, and how many prior different types of positive random variables you can represent as mixtures of exponential. Everything will fall in the framework, provided you can sample the latent mixing variables. Okay. In particular, you can do this for both VGL and graphical horseshoe, same framework as Wishart. All right. So here I will just I will just make one you already understand what we are getting into, but I'll just provide a one slide summary of what we had before for Wishart and what we have now for the situation of, say, Bayesian graphical lasso. So this is the on the bottom slide we have for Wishart, we have this normal times gamma. We still have the same thing. The additional quantity is this latent mixing tau that's in red. But conditional on tau, you still exactly have a normal times gamma. Now the prior covariance matrix C of that normal involves this latent mixing variable. But that's fine. The density that I'll evaluate is still the density of theta p given rest. And rest now involves this latent mixing tau. This tau needs to be sampled from the posterior, but the density of tau given rest will never have to be evaluated. And that's the key benefit. So if you can do this for Wishart, you can also do this for Bayesian graphical lasso. You can also do this for graphical horseshoe. You can do this for any normal scale mixture on the off diagonal, any exponential mixture on the diagonal. Your prior can be element-wise, the way you have described. Okay. So if you have an Wishart prior, you have a prior on the entire omega, right? So the property of the element-wise priors become hard to visualize. So because of that, this prior is actually much more, to me, it's interpretable, right? I can put an element-wise prior on omega ij and an element-wise prior on omega jj, and I can have some better handle on the element-wise properties. For example, if I believe I have a sparse entire of p by p omega, I would like to put a sparsity-inducing prior on the off-diagonal terms. But the difficulty that will come will be this positive definite restriction, this truncation. But now we have avoided that using Wang's sampling technique, and together with our Schur complement adjustment. And that's the main idea. So what we did is that, of course, in this situation, the truth is unknown, as in the Wishart case. If the true likelihood was, of course, also known here, then what we are doing would be kind of moot, right? We would not need this. So but still, what we can do is that following our technique, we plotted the log marginal for that lambda parameter, which is that's the prior hyperparameter. And for Bayesian graphical lasso, which uses a double exponential on the off-diagonal terms, and graphical horseshoe, which uses a horseshoe prior on the off-diagonal terms. Both use an exponential prior on the diagonal terms. So what we did is that, and then we plotted the log marginal likelihood against lambda. So it has a sort of a nice convex shape, and then we did a grid search to simply figure out where the maximum is occurring. So lambda naught is the green line, is the true value of lambda, which was 2 in this case, and lambda max is occurring at 1.91 and at 2.13. So meaning it is indeed giving us sort of at least the maximum MMLE, the maximum marginal likelihood estimate of lambda is sensible. And we calculated Bayes factor log. Now we can do this. We can calculate log Bayes factor. So if you proceed to either extreme, from starting as true lambda is 2, so there the Bayes factor is small. But if you take a lambda that is either too small or too large, then your Bayes factor increases, which means it provides so that if you're interested in using them in a Bayesian hypothesis testing framework, it provides sort of strong evidence against values other than 2. That's what we found. Additional results and implications. So the strategy also works, actually, it turns out. Now remember, so far we have just used continuous global local shrinkage prior, so there is no exact zero. So one situation where you do have exact zero is the so-called G-Wishart case. So there is an omega like Wishart, but there is an underlying graph or an adjacency matrix which says if the adjacency matrix, the element is 1, then the corresponding element omega ij element is non-zero. If the adjacency matrix element is 0, then the corresponding element of omega ij is 0. So it turns out this actually also works for calculating evidence under G-Wishart. So now for G-Wishart, there exists that method by Atakais and Massam, but only for G-Wishart. So we compared with that. It actually turns out to be quite competitive with Atakais and Massam. And as a byproduct, not only this, following our goal in this paper is marginal likelihood calculation, but we have been able to come up with a new row-wise sampler. So sampling from G-Wishart is also a hard problem, okay? Because you have to find these cliques and separators and so on and so forth. But our approach is entirely row-wise or column-wise, okay? We are not in the clique finding business, so we don't do this. We proceed simply starting from the pth row, do a Schur complement adjustment, sample the p minus 1th row, and so on and so forth. So the technique that we designed for likelihood evaluation, it certainly works for that, but it also results as sort of as a byproduct as a new row-wise sampler for G-Wishart. So I have a one-slide summary of that. The algorithm, I will, I thought I would have time to discuss this, but let me, I think we are kind of at the end of it, so I'll just skip it. So if you're interested in this new row-wise sampler, just take a look at the paper. But the key point here is that we avoid the maximal clique decomposition. And does it work? How do we know? So what we did is that we took a sort of a state-of-the-art sampler by Lenkowsky, which is and then G-Wishart. The key thing with G-Wishart is that your graph doesn't have to be a decomposable or a triangulated graph. It can be a non-decomposable graph. So what we have here is sort of the smallest possible non-decomposable graph, which is just a 4 cycle. Okay, 1, 2, 3, 4 with no edges in between, just a square sort of. And then we sampled using Lenkowsky's sampler, which is the current state of the art, and our method, which proceeds this row and column-wise manner. And the posterior mean based on 10K samples is near identical. And this is the smallest possible example that I can fit on one slide, maybe. We tried up to p equals 30. And the maximum difference, I think, in the Frobenius norm between Lenkowsky's and our methods that we saw were about maybe 2 units for the, so omega star hours minus omega star Lenkowsky, Frobenius norm of that was max upper bounded by 2.6 or something like that. Okay, so which tells us, it gives us valid results. And the key point is that our sampler does not require a maximal clique decomposition. Now, is that a good thing or a bad thing? It can be good or bad. So Lenkowsky sampler will work well if there is maybe, everything is connected. Then Lenkowsky can sample everything is one click, can sample everything at one go, and he's done. Okay, we won't be able to do that. We have to proceed row or column wise. Okay, last column, then the last minus 1th column, and so on and so forth. But Lenkowsky will suffer when there are lots of isolated nodes. So then clique finding is hard. All right, and you have lots of very small clicks, then Lenkowsky will suffer. And our procedure is actually kind of agnostic to that, right? It proceeds row or column wise. So it can be better than Lenkowsky, can be worse than Lenkowsky, depending on the connectivity of the graph. So our procedure is sort of agnostic to the connectivity of the graph. It proceeds in a row or column-wise manner. But if you don't have an a priori belief of the connectivity of your graph, our approach could provide sort of a good default starting choice for a sampling method. Okay. So with that, I think we are on time. So I'll try to conclude. So with based on all this, I hope to have been able to convince you that the strategy developed here is there is nothing specific to Wishart or Bayesian graphical lasso and so on. The distribution of the latent mixing variable is quite unimportant here. Rather, the key point where the strategy here will work is predicated upon just these two things. Okay, the priors on the off diagonals of omega, they have to be scale mixtures of normal. The priors on the diagonals of omega are scale mixtures of exponential. And these two conditions together can indeed describe a very, very broad class of priors that includes structured priors such as Wishart or G-Wishart, but it also includes more recently developed these kind of element-wise priors such as Bayesian graphical lasso, graphical horseshoe, and there are several other priors that follow the same framework, but we didn't talk about today. All of their marginal likelihoods can now be calculated, and hence the claim. So these are sort of fairly mild requirements and can handle a very broad class of priors. And now let's see how we can extend this. So far we talked about normal scale mixture prior, right? How about normal scale mixture likelihood? It's possible, right? So suppose you have a t likelihood. So y is marginally has a t distribution. So the margin, if your likelihood is marginally t, now you can write the likelihood conditionally as a multivariate normal, and then you have a mixing tau variable in the likelihood term, right? So this is, of course, the margin. It's a non-Gaussian graphical model, non-Gaussian. But now you have this t, you have this tau. So, and you have this set of latent variables anyway, because we are doing CHIB, right? So now just include this tau into your already existing latent set of latent variables in CHIB Z. And then using this, I think it should be possible to calculate the marginal likelihood of non-Gaussian graphical models where the marginal where the likelihood, okay, so the likelihood, not marginal likelihood, I'm sorry, the likelihood itself is a t, some sort of scale mixture of multivariate Gaussian. So it will give us some additional latent scale mixing variables. So it can be the technique, I think, can be expanded to handle, say, non-paranormal. Maybe it should be possible. Well, although we have not investigated that in this paper. Okay. So with that, I would conclude. So so the paper is currently submitted, but an archive version is available, and Sagar put up the code on GitHub. So if you're interested. And there are lots and lots of references, but these two are the main references on which the paper is based. So the first is the CHIPS paper, and the second is the Wang's sampler, not marginal likelihood evaluator, but sampler for the graphical lasso, Bayesian graphical lasso estimator. All right, I'm done. Thank you very much.
Thank you, Anindya. This was great. So do we have any questions? If you have any questions, please feel free to unmute yourself and ask directly.
Anindya, can you hear me?
Yeah, I can hear you. Hi.
Hi, nice talk, very clear. So as you know, I'm by no means an expert in this, but I wanted to ask, so so I'm recently interested in this line of work from the empirical based perspective, and I was wondering if you could, so are there methods where you try to find out the evidence using sort of by maximizing the elbow? Because at least in the variation and approximation community, that's a very common technique, right? And I think the usual criticism they have for this MCMC kind of methods is that it does not scale with sample size and so on.
Yeah.
Anyway, so I mean, I'm very new to this, so I wanted to hear your thoughts. And
so right, so the thing is, of course, elbow is what you would have to use, because evidence calculation is a hard problem, right? So when we do not have evidence, what is tractable is the elbow. So that's the thing we can optimize, and then it provides a evidence lower bound, so it provides a valid lower bound, so that's what we use. But then there are problems with elbow in the sense that variational approximation is not unique, so it depends on which variational approximation you choose, so on and so forth. Whereas this is marginal likelihood, so it inherits all the properties of the likelihood itself. So I think elbow is certainly possible, you can use it, but typically elbow, people go to elbow because they don't have the actual evidence. And computational scalability is an issue. That is always going to be there. In particular, our method is based on CHIPS approach, so it's an MCMC based approach, so it will inherit all the scalability issues of MCMC in some way. But still, as we see that variational there will be a problem with variational approximations too, right? So you might end up with an inconsistent estimate. So that happens, say, in state space models and things like that. There is a paper by Wang and Titterington. So yeah, so I think people haven't used, my feeling is that people haven't used evidence so far because it was not tractable. And if it is, there exist tractable algorithms that are reasonably scalable, maybe more and more people will use the actual evidence than a lower bound.
Okay, so if I may just, so this is something that you may know, one of my colleagues, Shumit, has a paper with Shubhobroto where they try to understand variational inference in high dimensional regression and so on, where they kind of essentially show that the elbow is actually maximizing the elbow for a mean field actually gives you the exact marginal density. And I was just wondering if these kinds of analysis have been done for Gaussian graphical models and other complicated problems, and how easy or how difficult they could be. Anyway, just thought. Sorry, yeah.
No, that's a good idea actually. To my knowledge, no, I have not seen. So yeah, so but then right, yeah. To my knowledge, I don't think it has been done. So it will be if you want to and take that on, that'll be great, I think. Yeah.
Thank you. Very clear talk. Thank you.
Thanks.
So we are right on time. Thank you, Anindya, again for this wonderful talk. Thank you for accepting our invitation to present this. Thank you, everybody, for attending again. We'll also be posting this talk on YouTube. So thank you all.
Thank you. My pleasure.
Thank you.
Bye, everyone.
Bye.